All right. Can you guys hear me all right? All right, thanks, Allison, for the thumbs up. All right, so yeah, as he mentioned, I'm going to present like a kind of high-level view of representing meaning of words and sentences in a vector form. Who am I? I am currently a PhD candidate at the Center for Spoken Language Understanding, which is a computer science department at OHSU. I believe it's going to no longer be a department at OHSU by the summer, but I should be defending my thesis in August, so hopefully that will all work out. Before I was a researcher, I worked in educational software at a number of like literacy education companies. All of my work has been done largely in SQL and Python. I worked a data analytics team trying to determine whether or not the kinds of like literacy metrics that we were collecting were actually useful for determining long-term measures of success in learning to read. So this is an overview of what I'm going to talk about. I'm going to present vector, like a vector space model as a way of representing word meanings, what we might want to do with those, how we might then move those on to including sentences, some examples of what I'm doing with this stuff in my own research. And then if for those of you who want to like do this sort of work in Python, some resources for building and applying sentence vectors in Python. I'm going to try not to discuss machine learning, except at a high level. This may make this talk really confusing, so feel free to ask questions. I don't mind being interrupted in the middle of talking. All right, so meaning's a bit slippery, right? Like but in natural language processing, it's useful to have a way to approximate what meaning is of a word, of a sentence, and specifically to be able to answer questions like how similar are these two words, these two sentences, these documents, for things like information retrieval, determining like the sense of a given word in a sentence. And an example of the sort of question you might want to ask, even though this is a deeply simplified question, is which of these words here have like a more similar meaning in everyday usage? Like we have cat, feline, dog, and computer. And so I would say, I mean, it seems on the face of it like cat and feline are probably pretty closely related. Cat and dog probably also as well, depending on how you feel about feline, maybe even closer than cat and feline, because dog's probably using like a similar register to cat. And computer probably is a very different word than any of the previous three. And it would be nice to be able to represent that in a way that's numerical, so we could work with that like as a kind of data we could process. So how would a computer know that these words are similar? And I suspect that any of you who've actually worked in NLP, this is going to be like deeply repetitive, but if people are interested in this stuff and they want to like experiment with any of this stuff going forward, feel free to drop me an email. I'd love to talk with you guys about any of this. So, all right. So there's this idea of distributional semantics. So we have these words, cat, feline, dog, and computer, and we have two reasonable sentences we might say about cats and dogs, that a cat has 4 legs and purrs, and a dog has 4 legs, but it does not purr. And there's this idea called the distributional hypothesis, which is, I feel like it's like one of those Mark Twain quotations where it's like, probably not Mark Twain. It's regularly like attributed to different linguists. But either J.R. Firth or Zelig Harris promoted this idea that a word is characterized by the company it keeps, meaning that you can get a sense of what a word means by the words that it regularly appears around. So how could we operationalize this in a way a computer could use it? Well, let's see. So the simplest version of this is just this kind of like term co-occurrence matrix. And so what you do is for some corpus that you have, like a collection of sentences, let's say this is all the sentences that we have about cats and dogs is just these. A cat has 4 legs and purrs, and a dog has 4 legs. You could then create this thing where across the top you have the words, and then across the side you have the words. And every time that they co-occur in a sentence, in our collection of sentences, we increment that co-occurrence by 1. And now I did not do this computationally, so these might not be the right counts. So if you see one you want me to change, let me know, because it would look better in the slides long term. But the idea here is that cat and dog actually have fairly similar representations in this space. You would pick one of these vectors. So so you could then represent a cat, for example, by this vector 1, 0, 1, 1, 1, 1, 1, 0, and dog something like 1, 0, 1, 1, 1, 0, 0, 0. And if you were to then like measure the distance between those vectors, which is typically done by measuring the angle between them, then those might be fairly similar words. But if we were to then have another sentence that was about computers like crunch numbers or something like that, then the co-occurrence matrix for that would be very different. It would include different words that were never seen in co-occurrence with dog or cat. And so that word in this space would be more distant than the other two. So yeah, we operationalize this using vectors. The idea is to capture the context that each word occurs in, and in this, vector space model, which is what this is called, words with similar meanings ideally appear near each other in this like vector space. You call it projecting your words into the vector space. And then you can then measure the angle between the vectors and there are lots of ways to like measure distance, but angle is nice because it doesn't, the sentences could be of varying length and it would still be something you could measure. And there are lots of ways you can change this, right? Like this is an old idea that people have been using vector space models to represent meaning in sentences or for retrieving data since the 70s. And so there's been a lot of changes to it. One thing you could imagine you could do is maybe some of these words appear more frequently in our corpus. For example, you'll notice all of our sentences have a and has and for and legs. Well, anyways, that starts to make this a pretty empty set. But let's just say that if we have some more sentences and they all have a and has in them, we might not want to weigh those as heavily when we consider like their importance as others. So one of like the classic ways is for those of you who are looking for things to investigate in natural language processing, the classic way of dealing with that is what's called TF-IDF, which stands for term frequency inverse document frequency. So words that appear all the time, like a and has, that would have a much smaller number than something like cat or dog that only appears in one sentence. And then another way to, and I'm not going to defend this right now, but if people want to talk about it, I would love to. Another way to make meaning of this is an idea that was developed in the 80s, the 90s, was this approach called latent semantic analysis, which takes what's called principal component analysis to determine which of these dimensions, like a cat has 4 legs and purrs, are the most important dimensions, and it reduces the amount of, it reduces the size of the vector to some arbitrary width. You could then represent your sentence instead of being the size of our entire vocabulary, 1, 2, 3, 4, 5, 6, 7, 8. Instead of all of our vectors being 8 dimensions, we could then say, have some arbitrary reduction to say 2. We could represent all of these by just their presence of cat or dog, for example. So, all right, so that's like a broad overview of what vector space, the vector space model is for semantics. But the real idea, and this is going to be true about everything we're going to talk about, is that what you're really trying to capture is, for any given word in this case, you're trying to capture the context around it. So the words that are in some neighborhood on either side of this word cat or dog. And in this case, the context is the entire sentence, but you'll see that there are other ways to do this as well. So you may have heard the phrase word embeddings. I put this here just because when I was first starting out, I was confused about the difference here. Are they different? No, a word embedding is essentially just another term for like vector space model of a word, but it's just in this, a word embedding is essentially implying that you're putting something in the beginning of an NLP pipeline. You need some kind of like fixed width input for your tasks, and ideally you're capturing some sort of sense of something about the language. In this case, like the meaning of the words. The most like famous of the current like word embeddings is this thing called word2vec, which was developed at Google by this Thomas Mikolov and presented as this as word2vec, which is short for, of course, word to vector. And it's part of a family of methods that instead of us creating this entire context, like term context matrix, instead uses a neural network to directly estimate a word representation. In this case, WordDevec, like one of the what it does that's sort of remarkable is it has a couple of different varieties, but the most interesting to me is you train a neural network specifically to use each word to try to predict its context. And so if it fails to predict, so the words around it. So in this case, we would give it, we're talking about the word cat, and we're just having a context of the word on either side of it. In real WordDevec, you'd use a larger context. But in this case, we're just going to talk about a context of the word on either side of our mystery word. And so in this case, you would try to predict a cat has, so that you would be trying to predict the two words a and has. So this has been sort of a wildly successful word embedding for a bunch of different applications. For example, it's good at things like word sense disambiguation. I don't know. You see it all the time in like as like sort of like the entry level, not entry level, but it's used everywhere for all sorts of different word representations. And it has an interesting feature that I think is worth mentioning, which is it has what's called linear compositionality, which means you can take a word in this vector space and add or subtract some other word, and you generally get a kind of it's through magic. You get a kind of the resulting vector is going to be relatively reasonable. It's not always true, but for example, on their original trained data set, they took Madrid, they subtracted Spain from it and added France, and the resulting vector that they got there was the closest vector to it was Paris. So this is sort of a useful fact when we start thinking about how we might turn these word embeddings into sentence embeddings. The next step here is we have a way of representing words. It captures something about their meaning. Can we expand this to create a representation of a sentence that is also captures something about the language of the sentence? And if so, what? So the simplest solution for taking these word vectors and making a sentence vector is you just take you take your set of vectors, like all the words in your sentence, and you sum them, and then divide the like piecewise in the vector by however many words were in that sentence. And this is called a bag of vectors approach, which is similar to, I guess I didn't close on here, but when we do this co-occurrence matrix, what we're doing is we're treating each of the words that occurs with it. We treat the context as a bag of words, the idea being that its order isn't captured. We're just capturing co-occurrence, right? So it's a bag, meaning it's just we have these things, we have some number of them. We don't keep track of order. And so in this case, averaging it over the vectors is also not it's not capturing word order. It seems reasonable, though. WordDevec does have this kind of linear compositionality, so we should be able to add them together and get some kind of like meaningful vector that should be, in theory, close to the meaning of the sentence. And it actually works pretty well. It's hard to quantify this. I will try in a couple slides to talk about, to quantify how well it works and why it works. But obviously, it has this massive limitation in that the word order is lost, which for some words, like, for some words, their meaning is largely like determined by context. I'm trying to think of a good thing, but something that has like something where the spelling is the same but the meaning is different. So either like synonymy or homonymy. What was that?
Negation also cares about.
Oh yeah, for sure. Yeah, or negation, right? So you need to know what is not in the sentence, and to do that without the word position is challenging. So it also feels a little bit unprincipled. Like a short sentence makes sense, like this one, crush your debt. I suspect you could probably represent as a word vector. But when you start adding more than, when you start getting like more and more accretion of words, or you start trying to combine sentences to make like a larger document out of them, it just starts to feel, it's hard to imagine what these vectors actually mean.